storage. That is to say, someplace to put your files. It's probably one of the most important aspects of running your own server. When you run out of it, you lose files. When you don't have enough to begin with, you lose files. And when you screw it up, you lose files again. We're going to take a stepped approach here. One of the great things about how Linux handles storage is that it's tiered. You build blocks, and depending on how complicated or how feature-filled you want it, you can build as few or as many blocks as you want. And coincidentally enough, the basic unit of storage in Linux is called block storage. Computer science in general looks at most of the storage that you use day to day as block storage. Hard disks store data in discrete chunks, which we call blocks. In Linux, the block devices are any type of storage unit that uses that type of chunked storage. So hard drives come to mind, DVD-ROMs, but not necessarily writable DVDs, and things like floppy disks or even certain types of network devices are all block storage. I've created a new virtual machine here that has a couple of extra hard drives just so that we can do the demonstrations for this segment. I mentioned before, kind of lightheartedly, that a lot of times I run commands mostly as root and don't use sudo all that much myself. When you start doing things like this and you know you're going to have to use the root account for a lot of different things, it really is okay to do something like sudo su, which will put you directly into the root account instead of having to prepend every command with sudo. Just be advised that there's no surer way to screw up your system than to run commands as root when you thought you weren't. Now we need to make the first disk that I added, which is SDB, useful. We're going to partition it with fdisk, which you'll find on every Linux installation. When you hit M inside of fdisk, you'll see a context menu with some help. And basically what we want to do is print the partition table with P, and then add a new partition. When I print it, there's nothing there, and that's a great sign because it means that we picked the correct hard drive to partition. If you saw something there, you would be wiping your data. We hit New, and then P for a primary. I'm just going to make it the entire size of the disk, so I basically hit Enter twice here. And then when we print it out, you'll see that we now have a partition. That's great. It means it's going to be usable in just a second. Hit M again, and W for write table to disk. Save it out. And now we have a new disk that we can work with. What this has actually done is created a new device in the dev tree called SDB1, which represents the first partition on disk SDB. We can technically operate on either of those devices as if they were block devices. But in most cases, you're going to want to work on SDB1 so that you're doing something to the partition and not the entire drive. There's some funkiness with working with the entire drive. So mkfs.extended4 is the same as format. When we hit enter here, it's going to create an extended4 file system, which we can then mount using mount or put into fstab. Mounting a file system simply means to make it available to the users of the system. You do that by creating a directory, and that directory is where you want the new file system to be located. In this case, I'm going to put it inside of /mnt, which is kind of the traditional place to put temporary mount points, sometimes permanent also. What you're really doing here behind the scenes is creating a directory, and then inside of that directory you're going to mount the disk, which means that instead of there being an empty directory there, there's actually an entirely new file system in its place. So we've created a directory and we want to make it available. So in this simplest version of the invocation for mount, you simply do mount the device name and then the directory where you want it to show up. As you compare the two listings here, you can see that SDB1 is now available and it shows enough free space and where it's mounted at. If we go into the directory, we'll see lost and found. That's created by the format, and you want to leave that there. Otherwise, it's blank, and all of the files in there would be owned by root. I can create the files, and as soon as we do it, you'll see that not only are they owned by root, but they're also zero size. The touch command creates a zero size file. If we unmount the disk while we're inside of the mount point for it, it's going to fail. So I go back up a directory, hit unmount again using the full path, and then use another DF, which stands for disk free. You can see now that it's unmounted again. If we go into the SDB directory, the three files that we made earlier no longer exist. It's exactly what we would expect to see. In this case, you can use any directory that you want. It's not related to the disk file name itself. Or that is, rather, it's not related to the disk device name. So dev stp1 has no bearing on where you put it inside the file system. You could throw it into /mount or into /var or wherever you felt like it, and it would still be accessible the same way. One thing to keep in mind is that when you do mounts like this, using the mount command just from the command line, they don't persist across reboots. If you want your new file system to be available when the machine boots, there's a special file that we have to edit called the fs tab. And each entry in the fs tab lists a mount point and the device that uses it. I'm using Nano, which is just a basic no-frills kind of text editor, and I'm going to create a new entry all the way at the bottom for this new device that we've just made. The easiest way to do it, until you remember it by heart, is to just steal an entry from the one above it. FD0 in this case is my floppy disk. Amazingly enough, my computer still has a floppy disk. Copy it, put what mount points you want in place, and then do Control-X to save the file. Once that's done, when you reboot the machine, it will automatically mount the device. At the same time, if you do Mount-A, it reads fstab as if the machine were booted from scratch. As soon as you do that, anything that isn't mounted at that point will be afterwards. And of course, now it's time to make things more complicated. Additional complication is easily achieved by using software RAID. We can add on software RAID functionality to our existing block devices. What software RAID does, in the simplest case, is allow you to take two devices and mirror the data onto both of them. Therefore, you can survive the failure of a single disk. So we're going to go ahead and create our first software RAID array device. The initial thing that we need to do is install an application called MDadmin. MDadmin, the MD stands for multi-device, is going to let us join together multiple devices into some sort of abstracted single device, a single block device. In this case, what we're going to do is create a RAID1 array, which is a basic mirrored configuration. While I'm doing this apt-get install, it's asking me to configure an email client because MDadmin can alert you when a device member in an array fails. Normally that's a good thing to do, but in this case I don't really care. While the installation finishes, it's going to generate a default MDadmin configuration file that's going to be basically good for nothing. It's not going to have any type of mirroring built in for you. You do have to configure it all by hand. But luckily, the tool itself makes it easy enough to configure that you shouldn't have too much trouble with it. Typically, the complication with MDadmin comes when you need to rebuild a failed array and not when you create it the first time. RAID configurations are broken into levels, whether they're software or hardware. The first attempt that we want to make here is a RAID1 mirror, where you literally mirror the bits onto both devices. So you do a write operation onto a RAID device, and the RAID driver writes the bit onto both devices that are underlying it. In order to do that, we need to change around the partition table on SDB. In the background, it shows a partition type of, quote, Linux for us, but what we actually need is something called the Linux RAID Auto Detect. So we go into fdisk again, delete our partition, just for good sake, recreate it, assign it to be full size all over again, and then we're going to issue a new command called T. You can see here that the partition type is defined as Linux. By default, that will always happen. But if we give it a T command, as highlighted here, we can change the partition type. In this case, Linux Auto Detect is going to fall in the lower right. It's type FD. And what we want to do is assign our new partition to type FD so that the MDadmin tools will discover it and be able to use it as a partition for their type of metadata creation and for a RAID array. The second thing that we have to do for this is create an identical partition table on SDC, which is a disk that I stealthily added and didn't tell you about. So it should be fairly straightforward to do that. We just fdisk SDC again and create duplicate settings on the new disk. So new primary partition, take up the entire disk, change the partition type to Linux Auto Detect, Linux RAID Auto Detect again, write it out, save it when we're happy. This time we're not going to format it. We're actually going to format the MD device, which then will write the bits to both disks simultaneously and invisibly behind the scenes. So using mdadmin --create, we feed it devmd0, which is the name of our newly created RAID array. And actually mdadmin will create it for us using that device name. So there's a lot going on here in this command line. mdadmin -- create dev md0. md0 is kind of the traditional name for your first RAID device. Once you execute the command, this device will exist, but it doesn't currently. The next set of arguments is RAID devices equals 2 and level equals 1. We're going to use 2 devices, obviously, but RAID level 1 simply means that we want to mirror. And then the last 2 arguments are the partitions that we want to mirror against. Now, as I've said before, bad examples can be instructive. So something odd that's happened here is that since we've already had a partition on SDB1, and when we repartitioned it, since it doesn't actually remove any data, the mdadmin program is warning us and saying, hey, you have valid data on SDB1 and we're going to completely remove it. That's okay in this case, but when you're doing it yourself and you get this message, if you know you've never done anything with the partition that you're trying to mirror, go ahead and say no. It'll save your sanity. And in the long run, it'll probably save your data at least once. I'm going to say yes because obviously it's a demonstration, and 2, there's no data on there that I care about, just those 3 text files from earlier. So you can see that it's created the array, and there's a file called procmdstat that we're going to check to see for the creation progress, which is basically 0 at this point. This status bar shows how far along the MD device is in copying the bits from 1 to 0, from disk B to disk C. Because the operation is a mirror and we didn't start with a blank slate. There's a way that you can do that, but in this case I didn't care because the data didn't make any difference. As a side note, and as for a demonstration, I'm going to create a script here that monitors the MD rebuild status. This is just a quick and dirty script in Bash, which is the command interpreter that we're using. It's going to cat the file every few seconds, in this case 5, so that we can see what the progress looks like. It's a very simple loop, but it's instructive to see if you just really need a quick loop done and you don't want to take the time to write something longer in Perl or even do anything really ugly in a longer Bash script. This will get the job done for you. As I run the script, you can see here that every 5 seconds it greps for the word resync, and it kind of shows you how far along it's been done. So it's done about 1% every 5 seconds. I'm going to super speed it up so that you don't have to stand through all this. By the time it gets to 99.3% or so, the script actually fails because there's no longer a word called resync, and so the grep fails. But I can tell by catting it by itself that it's done and it's ready to go. We can go ahead and get it ready to put some data on it now. Doing that is actually pretty standard procedure. You check to make sure the device was created successfully, and you can see that it is. From this point out, it looks to the system just like a hard drive. You format it the same as a hard drive, you mount it the same as a hard drive, you can erase it the same as a hard drive. The only thing that you don't have is a partition table on the device. Now that I've done everything that makes it a usable disk, I've mounted it really quickly. And you'll see from the DF that it's actually the same size as one of the single hard drive. So what's going on there? We're mirroring. And since we're mirroring, you only get the effective use of 1 drive instead of having the space of 2. It should be what would normally happen, but it might not be what you expected. Because of this, RAID 1 is actually the most expensive form of RAID. You have spent thousands of dollars on 1 terabyte disks. You've got 10 of them, but you still only have 1 terabyte usable space. You can lose 9 of the 10 hard drives and still have the data, but it's very expensive that way. Since we've got it set up, let's go ahead and use it. I'm going to edit FSTab again, and just like we did for SDB, because it's effectively just a virtual hard drive, we put in the device name, the mount point, and steal the default config from the other stuff elsewhere. You'll note that I accidentally left in SDB1 from the previous example. We're going to return to that in a second. If we do a standard mount/a, mount-a, it should put all of our RAID devices back in place. But we also get an error message about SDB1. Since I removed it, it's trying to mount it, but luckily it can't, or really not luckily, but by design it can't, because that device is already locked by the mdadmin utilities. So we delete the line, or comment it out in this case, do a mount-a again, the error message should disappear, and then you'll notice that we now have a RAID 1 device that's 20 gigs, and we're protected against a drive failure. But RAID 1 is expensive. So what if we needed a way to store a little more data using fewer disks? We had a little less redundancy and a little less speed, but it saved us a lot of money in the long run. And that system is called RAID 5, and it's been around for a long time. RAID 5 takes your data and stripes it across disks. Instead of mirroring every bit to an individual drive, it will dump one bit to drive A, and then the next bit to drive B, and the next bit to drive C, and then save a parity bit to drive D. That way you can recover from the failure of exactly one hard drive. In a lot of cases, this is actually the system that you want, especially for kind of a home server. If you buy 3 terabytes worth of disk, you get 2 terabytes worth of usable data. In the background here, I'm setting up a third drive, SDD, so that we can create a 3-device RAID 5 array using MDadmin. So I've recreated a blank partition table in all of the disks while I was talking, including SDD, which is going up here. Same concept, primary partition, full disk size, RAID auto detect. But instead of using level 1 and 2 disks, we're basically going to use level 5 and 3 disks. It's the only real difference. And then feed it the final disk also. So mdadmin -- create blah 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 blah. RAID devices equals 3. RAID level equals 5. And then the same rules still apply. It'll be just like a regular hard drive. You can format it. You can put files on it, and it will show up in dev or proc mdstat for its normal. Oh, look, I'm rebuilding. It will be immediately available, but you won't have data protection until the device rebuild is complete. And actually that's the same for the initial mirror. You don't have to let it finish completing, but if your data is important enough that you don't want to lose it in the event that you lose a hard drive between when the build starts and when it finishes, you should probably let it finish. Most times when you're building this out, it's not really a problem. I'm going to go ahead and format the RAID 5 array and not worry about it too much. If I were mirroring, which by definition means the data is probably a little more important, I may worry more. We're going to run the same old commands that we've already done before. Make a new directory, mount it in there, and make sure that the file system format worked. When we do a DF, there's going to be 40 gigs of available space. So we sacrificed 1 drive's worth of storage in order to get 1 drive's worth of failure. It's a pretty beneficial trade-off and something I would highly encourage you to do in any type of production server. And now that we've done that, let's make it more complicated. There's one more layer of block devices that we can create here. This is called LVM, the Logical Volume Manager. And what it lets you do is create block devices without knowing what size they need to be ahead of time. So you can either take a RAID array like we just did, or we can take a partition on a given drive, which is what I'm about to do, and assign it into a volume group. And inside that volume group you create devices that you can size and resize to whatever you need to. That means we have 2 more layers of abstraction, layers of block devices. We have the physical volume, which is a hard drive. We have the volume group, which is a collection of hard drives or hard drive partitions. And we have a logical volume. The logical volume, again, works exactly the same as a normal hard drive. You can format it, you can mount it. LVM specifically splits apart the idea of storing data on a block on a hard drive, and it lets you move your block storage onto multiple physical volumes on the fly without rebooting, or really without unmounting file systems or even affecting the programs. So LVM gives you a whole lot of power, and the configuration tools are uniquely simple. So the first thing we're going to do is create a new hard drive, which I've already done. I took the liberty of formatting SDB all over again. So I'm going to redo the partition table on SDB. Same thing as before, but this time instead of checking a RAID auto detect partition, I'm going to create a Linux LVM partition. As you can see, it's listed there under 8E. So I will create a partition of type 8E, which will now be a full Linux LVM partition, save it out, and we're going to go immediately into creating the LVM setup. First, we have to install the LVM2 package. It's called LVM2 because the Logical Volume Manager version 1 has long been outdated. LVM2 is going to install a set of utilities. The first of that we're going to actually use is called pvcreate. pvcreate, short for physical volume create, simply tags a physical device for use by LVM. It doesn't really do anything else, but it does change the data on the disk. So be careful what devices you run it on. Successfully created. Now I want to make a volume group. A volume group is comprised of a set of physical volumes. Oftentimes it's only going to be comprised of a single physical volume because you don't want your volume groups to span multiple disks. In this case we're going to do vgcreate, and then we want to give it a name. I personally like VG0. I use it almost everywhere. And finally we give it the physical volume that we just created. I can see all the volume groups on my system using VG display. There's one. It shows that the VG size is 20 gigs and that so far none of it has been allocated. There's some other useful things here, but for the most part you can ignore it for now. Once we've created a volume group, we want to start creating logical volumes, or LVs. This uses a command called lvcreate. They basically, once again, work exactly like partitions on a normal hard drive. Any operations that you would normally do on a partition you could do on a logical volume. With the exception that you can also resize logical volumes, which you normally can't do to partitions on the fly. The -- help here shows a lot of stuff, but for the most part you're not going to need it. The only things that really matter are the name and the size. I try to name my logical volumes after their function or at least their mount point. So you might have an LV named home or an LV named var. In this case I'm going to create a 4 gig logical volume and I'm going to call it something super creative, perhaps LV1. And the final argument that you give it is the volume group that you want it to be created in. In order to use it some more here in a little bit, I'm going to make multiple LVs out of the same volume group. That way I can demonstrate some of the other functions that you can do with it, like resizing and formatting. So now what you see if you do an ls in dev is a series of logical volumes created under a volume group. This is effectively the same as a dev SDB1, SDB2, SDB3. I'll format them all so that we can use them. And now that they've been formatted, I want to create mount points. Old hat right now. This is just to show you specifically that you can use these logical volumes literally exactly like a hard drive. They get mount points, they get file systems. One more command that's going to be really useful is lvdisplay, and it simply lists all the logical volumes that you have used on the system, including their size and what volume group they're attached to. When you display the volume group, you can see now that 12 gigs have been allocated because I made 3 4 gig logical volumes. And of course we want to know how to remove a logical volume. Once we get the list, it's as simple as using an lvremove, which will ask for confirmation. When you hit yes, all of the data on that logical volume as well as the device for it is now gone. All of this stuff about dynamic storage and logical volumes might seem overcomplicated if you're used to just installing a machine, setting up a hard drive, and letting the data go. But one of the things that administrators have traditionally faced through the years is not knowing how they're going to do their storage. Or more precisely, not knowing how users are going to use the data storage that's provided. LVM can help you correct this deficiency by letting you expand disk storage on the fly. If you have a mount point on home and it runs out of space, you can add another 10 gigs or another 50 up until the amount that's available for the storage group. To demonstrate this, I went ahead and blanked SDB again, created a new partition for it, and then I'm going to create a new volume group on it. Now we have yet another 5 gig volume. The first thing that we want to do is create a file so that we can make sure that it's still there after the extension. Otherwise, I haven't proved much of anything. VGDisplay grept for the proper string will show us that 5 gigs is in fact in use. So the next thing that we want to do is run lvextend, which will mark the logical volume as larger. So this doesn't change the underlying file system. It's a two-step process. But right here you can see that -L is going to increase with plus 8 gigs. So the new size is 13. It shows also in VGDisplay correctly, but it doesn't show up as a change on the mount point itself. To do that, we have to use the file system specific extender. There's resize2fs for extended 2, 3, and 4. There's also an xfs grow, and pretty much every file system has its own version. In this case, resize2fs just extends automatically to the largest possible size of the new file system. You'll see that it says performing an online resize. You can also do an offline resize if the file system isn't mounted. Of course, that means we have to take the server down, which is exactly what we're trying to avoid. The LVM command line tools are really useful, but you can also do all of this during the installation. So for the next couple of minutes, I'm going to go back and rerun through the Ubuntu server installation, but by setting up a RAID mirror and setting up LVM on top of it. I've created a new virtual machine that has 6 fake 1 terabyte disks. Which means that I'm using disk images, so I don't actually have all of these hard drives hooked up to anything. But what I'm going to do is create a RAID 5 group inside the installer, and then configure LVM on top of it in kind of a really generic but yet very expandable way. The next setup here is something that you might actually see in production one day. It's really pretty common. 6 disks in one machine, RAID 5 configuration. It wouldn't be such an issue to put this into a real production environment. You'd want to choose manual partitioning here, and remember that we're going to be working in layers. So the first layer that we have to do is take the 6 disks that you see and build them into a RAID array. The normal way of doing this is to create a single partition on each disk and then set the partition type to Linux RAID AutoDetect. The first thing to do with that is to go through each disk individually and create a new partition table, which is the default option that you'll get on any type of factory cleaned disk. I'll speed it up so it's less boring. One thing that's generally not safe to do is to put the boot file system on an LVM partition. When the Linux kernel boots, it has to read its kernel image and configuration settings from the boot file system, mounted at /boot. If you have that inside an LVM partition, it's very unlikely that it's actually going to be able to boot the partition itself. So you get the kernel load into RAM, it gets about halfway through, and then boot fails because it can't find the file system that it needs to get files from. In order to correct that, we're going to put boot on its own RAID mirror, but outside of the LVM configuration. I don't want boot to be part of the LVM config, but I do want it to be safe. So instead of having it inside the LVM RAID 5, I'm going to create a RAID 1 partition out of two 200 gig partitions on the physical devices. That way you have 2 copies of boot. The system can only boot from one of them, but in the event of a failure, you can fail over to the second disk that has your kernel and all your boot configurations. 200 megs is plenty for any type of boot configuration unless you have lots of spare kernels sitting around. On a production server you probably won't have that. You'll most likely have no more than 3. So I'm going to generate the RAID 1 mirror out of a set of 200 meg partitions. Since you're building up storage layers, one of the things that you want to do is define all of the RAID partitions first, so that when you're done with configuring all of the devices, you can go into the RAID configuration utility, define them all at once so you don't have to keep going back and forth rereading the partition tables. With the two 200s generated, I can go ahead and move on to the RAID 5 partitions. Notice here that you'll have 2 drives that are missing 200 megs worth of storage at the beginning of the disk. It really doesn't matter. Your RAID 5 configuration will use the smallest partition as kind of the baseline. So what I can do is just go through and quickly reconfigure all of the disks to have that one single partition that we're going to use for RAID 5. Ignore the difference of the 200 megs. I'll speed it up from here. All I'm doing is creating an individual partition on each disk. Once you're satisfied with the partition config, go ahead and go into the RAID configurator. It'll ask you to save the partitions to disk, write the partitions out. We're going to create our first MD device, that's multi-device device. Go to RAID 1. So this is the device that's going to be used for /boot. We pick 2, and then when we go into the drive selection, we're going to pick the 2 tiny partitions, the 200 meg ones that we made just for the boot. Once that's created, we're basically done. Go and create another MD device for RAID 5. And immediately one thing that we want to change is set the number of devices to 5. That's going to let us set a hot spare, so that if one of the disks fails, the server will go ahead and resync all of the data onto the spare device, alert us that the disk has failed, but without having the possibility of a double disk failure taking down the system. You have to select your RAID spare device separately, as just demonstrated. We're finished now. Go ahead and save it out, and we can move on to LVM, the next layer in the storage. With the additional complication, the next partition screen gets a little more confusing. Ignore any of the physical disks. We don't care about those anymore. What we do care about are the 2 RAID devices. The first, which is slated to be /boot, is going to be a normal file system, and we mount it at /boot. The next device, though, is an abstracted block layer device again, and we're going to use it for LVM storage. So pick the 4 terabyte partition, or whichever one you're using, and assign the type as physical volume for LVM. Then just hit OK. The partitioner will reread the partition table when we're done with the RAID configurations, and we can configure LVM afterwards. Once you've got your boot partition ready to go, go ahead and go to Configure Logical Volume Manager at the top of the boot menu. Save the changes out to disk, and start considering how you want your file system to look underneath of the LVM configuration. Kind of the general rule to follow here is that the more options you have to expand your storage, the more likely it is that it's going to meet your requirements in the future. So putting /home, /var, /user, any place that you might think you would need to expand storage in the future under LVM's direct control as its own logical volume means that you can extend them freely and independently of each other. Just like before, the first thing you have to do is create a volume group. I almost always pick VG0 because it's easy to remember and it's easy to tab through for auto-completion. Pick the 4.2 terabyte device, or whichever one you're using, assign the LVM to that, and then you can start creating logical volumes. My goal here, and hopefully one that you're pursuing, is to make the logical volume config as extensible as possible. So for every partition I create, I'm going to make a reasonable approximation of what I think the size should be. So a root partition size of 15 gigs is good. A home partition size of something that you think is accurate for what people are going to use is probably fine too. Remember, you can expand them at any time, but you can't make them smaller easily. So in this case, it's actually better to err on the side of caution than to give too much space to something that it's never going to need. The problem with that, of course, is that if you've never used Linux as a professional administrator or even at home, you probably have no idea what a production server is going to need in terms of space. The defaults that I've picked here are, I think, fairly reasonable. 10 gigs per var is great unless you're using MySQL, in which case, if you're using the default data installation directory, you're going to want to extend it. The home directory, 50 gigs, is great for a file server because everyone's going to have files that they want to use. Otherwise, feel free to follow my template here. I think that they're fairly accurate. I'm creating specifically a file server partition for use on the file and storage services later. I'm making it big enough that I think it's actually going to be usable. So 1 terabyte is a fair amount of file storage. And also, thankfully, the file server logical volume was the last one that I have to deal with for now. I'm going to go ahead and save this out, and suddenly things are going to get a little bit more complicated. We've added another layer. What you've got now is a storage system composed of multiple layers. You have logical volumes that are sitting on top of a RAID group, which is sitting on top of a set of physical disks. What makes this a little annoying is that when we go back into the partitioner installation, we're going to see all of the logical volumes that we just created, all of the RAID devices that we just created, and all of the hard drives. Once again, you want to ignore the stuff that we've already worked with. So just ignore the RAID config, ignore the drives at the bottom. And we want to go through and configure each LV device based on what we named it, and then configure it as that mount point. First up, I'm going to do file server. I like extended 4 because I pretty much use it for everything. The only thing that's different from what we normally would do is I want to put in a manual mount point. I like /file server just because it seems consistent. Again, you could put it anywhere that you wanted. For the rest of the list of logical volumes, I'm just going to go down through and assign them to the mount point, set them to be formatted for extended 4, and let it go. I'll speed this up again. Oddly enough, once you've done this Ubuntu or Debian install a few hundred times, this is about as fast as you'll do it in real life instead of speeding it up through the video. Very nearly done. At this point, I hit something I wasn't expecting. There was a bug in the installer, and the configuration that we'd already done for /boot had actually disappeared. So I had to go back in and reconfigure it on that 200 meg RAID 1 array from before. Here the installer is going to ask you a fairly interesting question. It says, you've got your root file system on a RAID device, which is true. And so you have two options on how to handle this. If a disk fails, your RAID array is going to be in a degraded mode. Since it's RAID 5, it's still going to continue to work, but one of the disks has failed out, which means that in a normal configuration, if a second disk fails out, your RAID array is going to break, and the machine is going to crash, everything is going to come crashing down around it. This is giving you the option to say, if it tries to boot and the array is degraded, stop booting. That eliminates your possibility of losing data because the machine isn't going to do anything with the failed disk. But it also eliminates your ability to fix it remotely because the computer is just simply not going to boot. In this case, I chose yes, allow it to boot because I plan to put monitoring around the disk. But if you don't have a way to monitor it, or if you just know, frankly, that you're not going to watch it, go ahead and say no. That way, if the RAID array degrades, say after a power failure, the machine's not going to boot at all. People are going to tell you the machine's not working. You can go, turn it on, nothing comes up. You'll have to hook up a keyboard and mouse, but you won't lose any data. And with the finishing of this progress bar, that concludes the introduction to LVM. I know I've thrown a lot at you, so here at the end I'm going to put in some quick Q&A from real questions that I've been asked by people throughout my career. Probably the most frequent and important question that I get asked is, I only have 1 or 2 disks, I don't want to use a RAID array, should I bother with LVM? It seems overly complicated for what I'm doing. You gain 2 simple things from using a single disk LVM, even without a RAID array. First, you have the ability to expand partitions exactly the same, so if you mess up or guess wrong on how you expect data to be balanced across partitions, you can move them and extend them as needed. The second is that when you do get a second disk, RAIDed or not, you can use a command called pvmove that will move the physical data from disk 1 to disk 2, or wherever you want to go, using LVM so that you don't have to go with tar archiving or something else to move them between partitions. Is it overly complicated? It's probably not overly complicated. LVM is not a simple tool, but it's designed for people who have needs in storage that are beyond just throwing in an extra hard drive. One of the key places where LVM shines is in virtualization, because you can increase hard drive size on the fly on virtualized environments. So you increase the drive size, then you increase the logical volume without ever rebooting. People also say to me frequently, hey, I have this motherboard and it's got built-in RAID, there's SATA drives, and you can configure it in the BIOS to do RAID 1. There is a big difference between onboard motherboard RAID and real RAID controllers. Real RAID controllers have battery-backed RAM, and they have complicated coprocessors that do the math in order to calculate the RAID stuff. Your onboard motherboard RAID controller probably, and depending on if you have a server board or not, but probably is what we refer to as fake RAID. And fake RAID devices you should probably avoid using one day you will lose your data, period. Also, they don't tend to work very well on Linux. So if you have a hardware RAID controller that costs more than a couple $100, absolutely use it. If you have fake RAID, don't. Linux software RAID is really stable. I have never actually lost a RAID array completely, but the rebuild process is definitely more complicated than swapping a drive in and out, which is what you get from a top-tier computer manufacturer's RAID controller. It's definitely worth looking at, but for the most part, Linux software RAID will do whatever you need it to do. This Linux storage model that I've introduced is probably one of the most complicated things that I'm going to cover. It's difficult, especially the first, second, third time. Just trying to keep in mind how the block system works, that you create a virtual block device out of block devices underneath of it. That's all complicated. Take your time, set up a virtual machine, do something where you can sit down, break all of this stuff, fix it, break it again, so that when you have this in a production box that's running in the closet somewhere, you aren't running around panicking trying to restore data but actually losing it by accident. As always, you can do some really powerful things with Linux storage. If you combine the right layers, set up the right services, and really pay attention to how they interact. You could do your own kind of SAN server. You could easily do an NFS server or something more simple, and file services really benefit from this.